Is it going? It's going. Good, good. All right. So, the artist asked me a question. He did. The artist asked questions. That's what they do in their careers. They ask a lot of questions, and then they create art as the answer. And he asked, and so this is sort of, I have not announced that we're starting degenerate perturbation theory, so when I announce that, then we'll do it, but I haven't announced it yet, so this means we're talking about non-degenerate perturbation theory. And he asked me, why is it that in the expression for the first correction to an eigenvector, you take the inner product of the zeroth eigenvector solutions with the perturbation operator A1 acting on the zeroth order perturbation, or the zeroth order solutions. But the sum you do is when you have values of n not equal to m. Okay? Now, first of all, if you look at this, clearly there's a problem if you let n equals m, right? Okay, but if you remember where this equation came from, we had beaten on some expressions, but then we had used the fact that we can express x1n as a sum of xm0, xn1, xm0. So this is just representing the vector xn1 in terms of the basis xm0, okay? And what's important is that we use this summation, this representation of xn1 in terms of a linear combination of xm0s in order to derive this. It was just one step, okay? However, in this sum, you go over all m, including m equals n. So the question is, how do you lose the m equals n term when you go from here to here? And the answer to it, interestingly enough, is that we set x equals x, the zeroth m vector, the zeroth eigenvector labeled by m, inner producted with the first order correction to n, equal to, sorry, this is when these are the same, equal to 0. Okay? Obviously then, the m equals n contribution to this, even though it's included in the sum, it's 0, and then it doesn't contribute to this anyway. Okay? So the numerator is 0, the denominator is 0, but who cares? Okay? What I want to do is just take a moment to explore this. Because it turns out that when he asked me the question, I didn't, off the top of my head, have the answer. Okay? And the reason I didn't have the answer is because I didn't actually specify when we decide this in my lecture material. But there was a point in the lecture material where I had some results, and then I said, and then they do some magic with them, and then they simplify to this. Well, in that discussion is this. So I'm just going to very quickly go over it. Okay? And this will also sort of re-warm you with material from last Tuesday, but it'll also hopefully warm you up for massaging things today. So what we can say is the following. So remember, x1n is a solution to a naught minus lambda naught 0 xn1 equals minus a1 minus lambda 1n xn0. Okay? So this is supposing we've already found the first order correction to the eigenvalue associated with the nth eigenvector, and now we just solve this to find the first order correction to the nth eigenvector. Okay, now what's interesting, this is a solution, but so is this. Can anybody see why this would be a solution as well? What does this satisfy? Does anybody remember?
It's a
It is, but is there an expression that it satisfies that's associated with this one?
If you just like put the y in there.
So a combination of a different row that doesn't change the determinant, multiple of a different row of the matrix doesn't change the determinant of that.
Well, actually, so this is what I'm asking you to recall, and it's okay if you don't. I mean, the material is kind of out there, but there is a similar expression satisfied. This is giving you the first order correction. This is the expression satisfied by the zeroth. And what is this equal to? 0. Yeah, that's the 0th order. This is just defining this as the eigenvalue of Ni. But think about it for a moment. If this satisfies this, then this is obviously also a solution of this. Because if you plug this y in here, you get this acting on this, which gives you this, plus this acting on this, which just gives you 0. So it preserves this equation. Okay? We on board? All right, now what's interesting is we can now take this and we can rearrange the following inner product. Okay? We can make this x0 n y1 n minus ax n 0. Okay? But this we can split up into xn0 yn1 minus a times xn0 xn0. Let me just pull a card. Oh! The artist. Please, with an artistic dance. What is this equal to?
That's equal to 1.
It's equal to 1, yes. It's nothing difficult about it.
Trivial.
Okay? So actually we can just ignore that. And we have this. Okay? Now this A is an arbitrary constant, right? It can be anything, and this is still a solution. Everybody on board? So here's a suggestion. Why don't we set A equal to xn0 yn1? Then what is this?
0.
It's 0. Okay? Now, I want to show you the impact of that. If we take the expression lambda 2 n, which was given initially by this expression, okay? How does this simplify given that this is 0? What happens? Can you see it? This is an operator, but this is a number. It's a constant. Does anybody see it?
It just becomes a1xn.
It becomes x n 0 a1x1n. Because this term just gives you this inner producted with that, which is 0. Okay? This was the simpler form of this expression that I said they wallowed around to give you. I don't know why I skipped that work. It was so simple. I mean, watch this. This is so easy. Check this out. This is so clean. It's beautiful. It's beautiful. It's beautiful. I can take this expression, lambda the third, the cubic term, the cubic correction, it's xn0 a1 minus lambda 1 n x2 n minus lambda n2 xn0, xn1. How does that simplify?
Are those all ends? Sorry.
They're all ends.
Okay, thanks.
This was this expression for the cubic correction to lambda, which is analogous in its form to the second and the first. Yes?
Wouldn't it just simplify to xn0 inner producted with a1 xn2? Is what?
Well, did we say that this is orthogonal to that?
Yeah, couldn't we eventually say that, I'm sure? We can't say that?
No.
Is there no beauty there?
No.
We can still do it.
Well, this disappears, right?
Yeah, this is it.
Yeah, this goes away. So there you go. Yeah.
Don't we still get like a 0 divided by 0? That's kind of bonks it up.
Okay, when I said there we go, I was lying. Because I don't know if you remember, but the expression for the cubic correction to the eigenvalue actually did not have x2 in it. So there is some more work we can do, and it's the following. First of all, this is a Hermitian operator, so we can bump it over here. And then we can use the expression that is analogous to this, but to higher order. Okay, so we're going to use, and I'm just going to write the result because I'm running out. I don't want to spend too much time on this. But we can replace this with the following. Minus a0 minus lambda n0 acting on x and 1. Actually, no, I'm using this one for now. X and 2. Okay, all I did was I took this right here, which is the right-hand side of this, and I replaced it by the left-hand side. Okay? Now we can move this Hermitian operator over to the other one. And now we can use the higher order expression that a0 minus lambda 0 on x2 is minus a1 minus lambda 1 on x1 plus lambda 2 x0. That's just a higher order version of this to replace this with this, and then that gives us xn1, a1 minus lambda n1 on xn1 minus lambda n2 on xn0. And now how does this simplify?
The last bit's gone.
The last bit's gone. Okay. So in the end we get which was our joyous statement that the cubic correction to the eigenvalues you can get if you only know the first order correction to the eigenvector. Okay? This is a blue boxed equation on last time, so don't think you need to write it down again. All right. So,
Sorry, Alex, before you move on, could you just talk conceptually for a second about the top left expression, the fact that our correction to eigenvectors is some constant times other eigenvectors in the same space?
yes.
Doesn't include our original eigenvectors. I'm not sure why it doesn't really make a lot of sense as far as wouldn't you just take our original eigenvector?
No. So this is the first order correction. These are the zeroth order solutions
Right.
that we're writing in terms of.
It doesn't include the eigenvector that we're even looking to perturbate around. So you're saying that solution is just a constant times some other eigenvector?
Yes. Yeah, I can't really think of a way to think about this other than this, solution generating the story up there. I mean, it's a pig. It's not four pigs. Oh my goodness. Okay.
Yep.
All right, so now we're going to go non-degen on its ass, and the degenerate, we're going to go degenerate on its ass. And the degenerate story is in many ways horrific, and I'm probably not going to go all the way through it. But I'll get to a few corrections and then just work through an example. But hopefully I can at least get on board the idea of why degeneracy causes so much of a headache. So first of all, let's recall what I mean when I say degenerate. Okay? So Zan, explain to me what is happening if I have a degenerate matrix.
So there's eigenvalues that are the same, one or more of them.
Yes. So if I have an n by n matrix, how many eigenvalues does the matrix have?
N?
Yeah, it has n eigenvalues. And if for it to be degenerate, what must be true? You just said it.
Yeah, more than one of them has to be the same. So
Well, some of them have to be the same. So maybe, 4 of them are the same and the rest of them are distinct. That's degenerate. Okay, they could all be the same. Or a pair could be the same, another pair could be the same, so forth and so on. Okay? So this is a statement about the algebraic multiplicity of eigenvectors. Remember, the algebraic multiplicity is how many times that is a solution to the determinant of the matrix minus lambda times a then equals 0. Have I got a fly in my hair? Shit, you tell me, right?
My glasses were just sitting weird and I need a minute to fix it.
Okay, that's fine. I just worried that I had a fly in my hair. But you guys
There
let
could
me
be
know.
one.
Seth, you got a fly on your head.
Yeah, I wouldn't know.
Okay, anyway, we're not referring to anything. If you don't think that's funny, you need to go and watch videos from last night. Anyway, and then geometric multiplicity. What is geometric multiplicity talking about?
Oh, that was that funky one that I never heard of before.
So here's a question. If I have n distinct eigenvalues, is there even a possibility of geometric multiplicity? No, because how many eigenvectors, if I have a single eigenvalue, how many eigenvectors must I have? At least one, okay? If it is a distinct eigenvalue, how many eigenvectors are associated with it? Only one. If the algebraic multiplicity is larger than 1, if an eigenvalue is repeated 3 times, how many eigenvectors are associated with it?
At least one.
At least 1 and up to 3. But you don't have to have more than 1, it just depends on the matrix. Okay? So when we're talking about degeneracy, we're talking about matrices which have repeated eigenvalues. Now, now here's the thing, if we're dealing with a normal matrix, and normal means a lot, it's not just a word, it's a plain old matrix. No, it's normal. Okay, so A dagger A, or A dagger and A commute. Then we know from theorems that follow from this that the space, or that the set of eigenvectors span the space. Okay? The eigenvectors span the space. Now I've already mentioned that if an eigenvector is distinct, then it has an or if an eigenvalue is distinct, then has an eigenvector associated with it. If an eigenvector is degenerate, and it's a normal matrix, then the geometric multiplicity has to equal the number of eigenvalues, or the number of times that eigenvalue is repeated. Okay? So if I have an eigenvalue that's repeated 3 times, then I have to have 3 eigenvectors associated with it. And the difference is the following. When we have a single distinct eigenvalue and its associated eigenvector, I'm trying to find the basis in a one-dimensional space. Okay, yeah. Here's the space. What's the basis? Okay, yeah, it's got to be a line like that. All right, and then any vector or anything in that space is a multiple of that. Okay? However, if I have two eigenvectors which span the space, is there freedom in choosing the basis?
Yeah.
Yes, there is. I could pick that as my basis. I could pick this as my basis. I could pick this as my basis. Okay? And you should have found this in solving for eigenvalues and eigenvectors. Okay? In the homework. All right? If you have a degenerate eigenvalue, then you often have a choice in figuring out what the eigenvectors are going to be. If it's a distinct eigenvalue, then there's only one choice, as long as it's normalized. Obviously, you can rescale it. Okay? All right. Now, here's the interesting question. Suppose I have a matrix A naught, which is degenerate. That is, some of its eigenvalues are repeated. Okay? Now suppose that I perturb it by some other matrix A1. Can you imagine the perturbation breaking down the degeneracy of the eigenvalues?
What does that
Yeah. Well, what it means is, if I start with A naught, which has degenerate eigenvalues, and then I just add something epsilon times another matrix to it, are you guaranteed that this new matrix, which is the sum of these, is also going to have degenerate eigenvalues? And the answer is generically no. There's a tiny chance it might, but generally no. I mean, if you want to write down a matrix that has degenerate eigenvalues, you have to be a little bit careful. And then if you want to add something to it that's going to keep degenerate eigenvalues, you got to be real careful. Okay? So in general, even if the initial matrix that we start with is degenerate, the total perturbed matrix might not be degenerate. Okay? Now, if you think about it, that's a bit of a problem. For the following reason. Remember how we do perturbation theory. The first thing we do is we take the unperturbed matrix and we find its eigenvalues and its eigenvectors. Okay? And then maybe there's a set of them. A set of n of them if this is n by n. And then we introduce, and I should say that when the theory was non-degenerate, these were uniquely known. These were unique, as were these, okay? And then we played around with introducing the expansion of the lambdas and the x's and then cramming it back into the defining equation. And what we found was the higher order corrections to those, okay? Now here's an interesting observation. If A naught is degenerate, then you can solve for the eigenvalues, but it might be that an eigenvalue is repeated, in which case the associated eigenvectors are not unique. However, their corrections might be unique. So we run into this weird thing where the data we're trying to start with includes a set of a basis of eigenvectors which aren't specified for us by the problem. These are always arbitrary as long as they correspond to a degenerate eigenvalue. But under the perturbation, they do have a preferred basis. But we don't know that from the start. Okay? It wasn't an issue in non-degenerate perturbation theory. These had a preferred basis. These had a preferred basis. It was just a stream of a story. Okay? So this is sort of an unknown in the degenerate perturbation story, which is a headache, but we'll fight our way around it. Okay? So here we go. Degenerate perturbation theory. Suppose that A0 is degenerate or has a degenerate eigenvalue. So I'm going to do like last time, and I'm just going to focus on a single eigenvalue at first. With m associated eigenvectors, okay? So the m here is a label which is telling you how many eigenvectors are associated with that eigenvalue. So this is actually labeling the degeneracy of the eigenvalue. And you know that if this appears 3 times, if it has algebraic multiplicity of 3, then there are 3 eigenvectors associated with it. And we're just going to call those Ymi, where I runs from 1 up to m. Okay? Now, we know that A naught Ymi 0 is equal to lambda m0 Ymi 0. That's just a statement that this is an eigenvector of this operator with eigenvalue lambda m 0. That's just an eigenvector equation. Okay? And now what we can say is that if we're going to perturb the matrix by some epsilon times A1, then we might expect that the corrected version of the eigenvalues and the eigenvectors can be represented in terms of an expansion. So I'm going to start repeating the story that I talked about last time. I'm just going to assume that we can do a Taylor series expansion of the eigenvalues and a Taylor series expansion of the eigenvectors in terms of this small parameter epsilon. Okay, epsilon is the thing that we're using to keep the perturbation small. So higher order terms matter less and less because they have higher powers of epsilon. Okay? Does anybody notice the absence of something peculiar in that expression? Is anybody bugged by it? Everything has comma I except for what? This lambda n. Is there any point in putting a comma I on it?
Well, it's going to be the same for all
It's the same for all of the i's. It's a degenerate eigenvalue. However, the corrections, as I mentioned, might be distinct. And we're just going to assume that they are. Okay? And so the corrections to lambda are going to have to be labeled by which they're corresponding to. Okay? So are we on board with this? Okay. So let's take this and let's shove it into the equation. All right. And if we shove it in and we do some rearranging and some relabeling, this is going to look a lot like what we did last time. We're going to end up with the following results. think I don't even have to write up A3, or the third term, because we won't use it, but. Okay, and then there's a third term which carries the story on. It's in the notes, but I don't think we're going to use it, so I won't write it up there. Now, I want you to remember that I may say to you, okay, this is simple. I just solved this one for the lambda, and then I plug the lambda in, and then I find the eigenvector, and then I take the eigenvector and I plug it into this one along with the eigenvalue here, and now this has got these two unknowns, and I can find the first order correction to the eigenvalue, and then I can find the first order correction to. Wait, does that make sense? Remember, there is a freedom in these. Okay? Because these correspond to a degenerate eigenvalue. So just because you're solving this doesn't mean you're going to have a unique solution. Okay? So we have to play around with that. So let's see what we can do. So first of all, what we can do is we can pick a basis of eigenvectors associated with A. So we'll just call them x0 and I. All right? And then with this basis, we can expand the correct expression for y, which will be compatible with the corrections, in terms of this basis. Okay? So this is the corrected basis. This is just an arbitrary basis. You're just going to find the eigenvectors or their relations, and then you're just going to pick a set. Okay? And then you just should realize that if you've picked a set of eigenvectors spanning the space, any other vector in that space, any other eigenvector in that space can always be written as a linear combination of those. Okay? All right. Now, of course, we'll pick an orthonormal basis. That's the obvious choice. So we'll take these to be orthonormal. And we can also set it up so that these are orthonormal. And now, the question is, how do we take this information here and try and reduce it so that there's only one unknown instead of two in each equation? It's like this equation has yn1 is an unknown, but also lambda 1 is an unknown. This has y2 is an unknown, and lambda 2 is an unknown, even if you know everything else. How can we take these and reduce them to an equation with a single unknown? Don't make me draw, I'll draw a card. Ross! How do you think we can reduce the number of unknowns that we're working with?
Probably through symmetries or elimination.
No?
Yeah, I'm sorry. It's hard for me to follow along with the lecture notes.
Okay, so let me try Madison, 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 Madison. Sam. What can we use to sort of reduce the stuff? We used it last time.
I can try again if you want me to.
Okay, go for it, Ross.
So essentially, we can express the unknown vectors y0 of n. What is it? Is that y0 ni? Is that what that is?
Yes.
And we can express them in terms of the basis of the original eigenvectors of a naught.
Yes.
Yeah, and then the unknowns are just the coefficients on these eigenvectors, so that we can reduce the number of unknowns that way.
Huh. That's not really what I was asking. Okay, don't worry about it. Don't worry about it. Okay, so I'll bring your memory. So last time we started with expressions like these, which are just taking the defining equation and shoving in these expansions and then rearranging terms. That's all it is. Okay? But if you look at these, they remind us of a theorem that we covered last Thursday, which was that theorem about whether a solution to this exists or not. Remember, you have this particular form of an operator, a matrix minus its eigenvalues times some vector, is equal to, overall, another vector. What must be satisfied by this vector in order for a solution to exist? It has to be orthogonal. To what?
The solution to the adjoint problem.
The solution to the adjoint problem. Okay, now I'm not going to write this up on the board, but the adjoint problem is identical to which problem?
The regular problem?
This problem. Because this is a Hermitian matrix. Its adjoint is the same as the matrix itself, and the eigenvalues are real, so their adjoints are the same. So the point is that in order for this to have a solution, this must be orthogonal to that. Okay? But that means that the inner product of this with this must be 0, which gives you an equation with only one unknown. And then we can play the same game with this expression. Okay? So here we go. I'll remind you what it looks like. So instead of using y, I'm just going to use the thing that I've actually found. The x0. Okay? But this must be orthogonal to all of the y's. And therefore, it must be also orthogonal to all of the x's, because this is the basis for a space, and you're saying this is orthogonal to the space. Well, this is also basing the space, so you have to be orthogonal to the space based by this as well. So we can say x0 ni inner producted with this equaling 0 guarantees a solution. Okay? And in fact, this doesn't have to be I. This could be j, and this can be true for any I and j.
Is J related to what we
So these are the eigenvectors associated with an nth degenerate eigenvalue. So these are all going to have the same eigenvalue at 0th order, but there's several of them. And so this J is just labeling which of those several you're talking about, and this I is labeling which of those several you're talking about. Okay? Now, we can take this and we can say, all right, this we can write as the sum. So this can be written as sum of k, x0, nj, a1 minus lambda 1, ni, aik, x0, nk. Okay, that's just writing this in terms of an expansion in the x's. And I'm using k as the summation because j is already sitting there. I don't want to know their j there. Okay? And I realize this is a horrible journey into subscript notation. And so I promise I will clean it up with an example in just a minute. Because it really is kind of grotesque to observe this in notation. Okay. I really don't know why I didn't just erase this and put that outside. I'm stupid sometimes. But anyway, okay. We can rewrite this as sum over k, x and j, 0, a1, x and k, minus lambda n, 1, I, delta jk, a, I, k, equals 0. And now, if you squint your eyes and you stare at this for a moment, you should realize this is just an eigenvalue problem. So what I mean is, I can take this and I can let it define the njkth element of a matrix M. Okay? All right? And then I can take the mjk and realize that the mkjth element is given by xnk0, a1, xnj, 0. Okay? Oh, sorry, this is the 0. All I've done is I've taken this and I've flipped it. I've transposed it. Wait. Did I transpose it? Oh no, the A1 goes here, right? Doesn't A1 go there? If I'm just taking this and I'm flipping it?
Is it adjoint?
A1 is self-adjoint. Okay, we're always self-adjoint perturbating. So we can actually take A1 and we can put it over here if we want. Okay? Oh, wait a minute.
Isn't that what we started with?
When did we define A1 as self-adjoint? I don't remember this. We defined A not as self-adjoint.
We're going to define A1 as self-adjoint as well.
Okay.
Yes. Okay. Otherwise, all of our correction, all of the use of Hermitian properties is going to fall out of the perturbed story. And trust me, we want those properties in there. Okay, so hold on, let me see. myself. Wait, hold on. Yeah, I'm confusing myself here for a minute. Oh, yeah. Sorry. I want this here. Oh boy, this is giving me a headache. Oh God. Hold on just a second. You can do this, Alex. You can do this. I don't trust you, Alex, at all.
Why are we transposing this? What is the?
Well, I was trying to show that MKJ is itself a Hermitian matrix, but let's just accept it, and then I'll get the details straight.
Sure.
Okay? So, sorry, I don't know why I can't read my notes. But anyway, this is it. This is Hermitian. Well, we'll just keep that there. Okay? So with that in mind, we can write this in the following form. M minus lambda 1 Ni acting on Ai equals 0. Okay? Where basically I'm taking an element of k. Just pick a k, and then you can show that this whole thing vanishes. So, and again, don't worry about following this. I'm going to work through an example, and hopefully that'll put the pieces together for you. But yeah, okay. So let us imagine that we solve this. Right, if we solve this starting with the matrix M, okay, defined here. If we solve this, we'll get, first of all, the eigenvalues. But that's the first order correction to the eigenvalues. So the first thing we're going to get is the lambda 1s. Okay? Number 2. We will end up with these coefficients, aik, which means we'll know how lambda 0 is to be expanded in terms of the basis that we started with, which is just some arbitrary solution, okay, with no special properties. Furthermore, what we've done guarantees a solution a naught minus lambda 0 n y n I 1 equals minus a1 minus lambda n I 1 y n I 0. Okay? So just using this one equation, okay, hitting it with an element of this space, an arbitrary element of this space, and then demanding that the inner product vanish, and this is just the requirement that these have a solution, we get all three of these properties. Okay? So now let me wander through quickly an example. It's not very long. Just to show you what this looks like. Whoa. And I'm going to erase this and hopefully keep that on the board. Yeah. Okay, here we go. So let's start with A0 equals 1, 0, 0, 0, 2, 1, 0, 1, 2, which I can immediately tell you has the following eigenvalues. With corresponding eigenvectors x0, 1 equals again, with the degenerate case, as usual, we find that we have the freedom in picking certain elements of the corresponding eigenvectors, but with the distinct eigenvalue case, we are not. All right? I do want you to notice that even though these are arbitrary, they're still orthogonal to that. Okay? And if we pick appropriate A, B's, and C, D's, these can also be orthogonal to each other. Okay? Now, these things I will call lambda 2I, where I equals 1, 2. That's the notation that we're using. This is a twice degenerate eigenvalue. It's 1 and 1. And so we're going to label it like that. Okay? So it'll fit into this scheme. All right? And now we're going to perturb this by the matrix A1, 0, 0, 0, 0, 0, 1, 0, 1, 0. Okay, nice Hermitian perturbation. The first thing I want you to notice is that if lambda 3 is distinct, then we can use all the tools from last time. So for the first order correction to lambda 3, we just say x3, 0, A1, x0, 3, and that gives us 1, okay? If we just take this vector, multiply it by this matrix, and then do the inner product with this vector again, that gives us the first order correction to this eigenvalue, and it turns out to be 1. We can also get the first order correction to the eigenvector and the second order correction to the eigenvalue, but I'm not even going to mess with that. It's on the paper. For lambda 0, 2I, consider this matrix, okay? MJK equals x2j 0 a1 x2k 0. Okay? I mean, n is just equal to 2 in this case. All right? Well, wait a minute. Hold on. We have a starting basis, so we can actually evaluate this thing. And this just comes out to minus 1/2, 1/2, 1/2, minus 1/2. Okay? Realize that this would be 2, 1, and this would be 2, 2. If we're using this same NI labeling for these. Okay? All right. Now we want to solve m minus lambda 2 I1 AI equals 0. To find the eigenvalues, we do the determinant. And that gives us it actually simplifies rather significantly. There's no constant. Therefore, our eigenvalues, or our eigenvalue corrections, come out to be 0 for the first of the degenerate eigenvalues, and, as it turns out, minus 1 for the second one. Okay? How many of you are following what I'm doing here? Raise your hand. Okay, it's fine that a lot of hands are not going up. Look, this is an eigenvector equation. M minus its eigenvalues times an eigenvector equals 0. That's the defining eigenvector equation. So we're solving it. The first thing we have to do is find the eigenvalues.
Yeah.
So we take the determinant of the matrix, and we set it equal to 0. This is the determinant of the matrix. Okay, I mean, you know, this is the matrix M, and then you're subtracting lambda from these. Okay? And now I'm just rewriting this, and it ends up in this simple form. But this is basically lambda plus lambda squared, which is lambda times 1 plus lambda. So one of the solutions is lambda 0, and the other solution is lambda is minus 1. That's all that's happening. But these correspond to the first order corrections to lambda. Okay? On board? Yes.
You just arbitrarily chose which one was lambda 2, 1 and which one was lambda 2, 2?
Yeah, sure. That was this assignment up here.
Okay, but I mean, like for the first order correction, you also just arbitrarily chose which one was the first and the second correction? How did you distinguish lambda 2, 1 and lambda 2, 2?
Hold on just a
Did you
second.
set lambda 2, 1 to negative 1 and lambda 2, 2 to 0? So that-
Pause for a second.
Okay.
Pause. Hold on a second. I can't remember off the top of my head how I identified this with this.
Okay.
Oh, shit. I'm sorry. You're saying, why am I associating this with this one and this with this one?
Yeah.
These are the same damn thing.
Okay, but so it's just arbitrary.
It's yeah, it's arbitrary.
But then later
Sorry.
on, if you have like a second order correction, how would you know which one goes with which? Because you need like.
Well, the
consistency.
procedure for finding a second order is using these.
Okay.
So you'll know what it's
that'll
associated
portray
with.
through. Okay.
Yeah. Sorry about that.
That's fine.
Okay? All right. At any rate, let me just quickly run through this. I go ahead and find the eigenvector corrections. No, sorry, I found the eigenvalue corrections. Oh, yeah. So I'm going to erase this. I don't think I need it. I think we're running late, so we're going to get this done. Because I want to get the hell off this subject starting next week, so sorry. So if I want to take lambda 1, 2, 1, and now plug it into this expression and find the eigenvector associated with it. Okay, I just take the matrix and I subtract the diagonals times the eigenvector associated with lambda 2, 1. Then I have minus 1 half, 1 half, 1 half, minus 1 half. Because that's subtracting 0 from the diagonal. That's not doing a damn thing to the diagonal. AB is equal to 0. And this tells me that minus 1 half A plus 1 half B equals 0, or 1 half A minus 1 half B equals 0, which is altogether telling me that A is equal to B, or that 1 over root 2, 1 over root 2 is the matrix of corrections. And then similarly, if I do lambda 1, 2, 2, then I end up with 1 over root 2 minus 1 over root 2. Okay, you can just plug this eigenvalue into this expression and find the eigenvector. And that gives me the corrections 2. So that means that the appropriate eigenvector, which is aligned with the corrections due to the perturbation, is given by okay, 1 over root 2, 1 over root 2, 1 half minus 1 half. Okay? This is just taking a selected assignment of A and B that's normalized. That's why I got the 1 half and the 1 over root 2's in there. Okay? And this turns out to be the eigenvector that will be compatible with the corrections. All right? And similarly, we can calculate y22. And that ends up being 0, 1 over root 2, minus 1 over root 2. And I just want you to notice, this was distinct. There was no arbitrariness in picking it. There was arbitrariness in picking these until we aligned them with the corrections, and in which case we got these. But notice, this and this and this form an orthonormal set, as we expect. Okay? So I started with the choice, this is 1 over root 2, 1 half minus 1 half, and I also chose this to be 1 over root 2 minus 1 half, 1 half. These are all 3 orthonormal as well, but these two, it ends up, are not aligned with the corrections. These are. Okay? So at the end of the day, I can check whether my work made sense by actually just evaluating for A equals 1, 0, 0, 0, 2, 1 plus epsilon, 1 plus epsilon, 2. I can evaluate the eigenvalues of this. And it turns out that this is actually quite straightforward. And in fact, this comes out to be lambda squared minus 4 lambda plus 3 minus 2 epsilon minus epsilon squared, which has a solution 2 plus or minus epsilon plus 1, which has 2 solutions, 3 plus epsilon, or 1 minus epsilon. Oh. Where did my corrections go? I erased them. Shit.
They're gone.
And we're so confident.
They were right here.
Yes.
Okay. Well, at any rate, if I picked the eigenvalue, shit.
Wasn't it 0 and negative 1?
Oh, yeah. So as it turns out, so lambda minus 1, so lambda 1 is an eigenvalue. And this gets no corrections. And that was what I found, but I erased it over here. That lambda 1 was 0. And then for the other one, it was minus 1. And then for this guy, it was plus 1. Okay? So it all works out. Now, to go on and actually try and figure out how to find the first order corrections to the eigenvectors and the second and third order corrections to the eigenvalues is a bit of a headache, and I'm not going to push you to do that. It's in the chapter in the book if you'd like to read about it. It's up to you, okay? But I'm not going to expect it of you. Are there any questions before we go today? Thanks for hanging with me. I really wanted to get done with this perturbation theory stuff. Next time we're going to go to infinity and beyond.